Hello, today we're going to talk about absolute entropy and entropy change. So remember that we use the letter S for entropy, and it refers to the amount of disorder, or chaos if you want to think about it that way. But there's the second law of thermodynamics, and it states that the entropy of the whole universe will increase if a reaction is spontaneous or a process is spontaneous. If you have a process that's at equilibrium, then the entropy of the universe is constant. We're not going to really focus on the entropy of the universe, though. We want to look at the entropy of specific systems. So remember when we were talking about enthalpy, we looked at the system versus the surroundings, and for an exothermic reaction, the heat was released to the surroundings, and an endothermic reaction, the heat was absorbed by the system. So we're going to focus on just the system when we're looking at our entropy. Okay. So the equation that we need to find for the entropy change in a given process is that we have delta S of the reaction or the process is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. Now this one should look kind of familiar because you can do a very similar thing for enthalpy if you know the heat of formation. Okay, if you have the standard heat of formation of the products, add them up, and then you can subtract the sum of the heats of formation of the reactants. So that formula should look very familiar to you guys. Let me go ahead and get rid of that because we're not dealing with enthalpy today. A few things I want to point out. So this is the overall enthalpy change for the process that we're looking at. And this indicates that we're at standard conditions. And so for us, we're going to deal with just 1 mole of our process. So for when we were talking about entropy, we said that the unit for that is joules per Kelvin. When we're looking at for standard conditions, it's joules per mole Kelvin. And so this is the unit that you'll see most of the time. Kind of like with enthalpy, you'll be dealing with kilojoules per mole for the most part. Because we're looking at a standard enthalpy is for 1 mole of the process or the substance or whatever is going on. So the big difference you want to notice is this is in kilojoules, this is in joules, and entropy also depends on the temperature. So just kind of pay attention to the units and be careful there. Okay, so here's an example, a very, very representative question of something you might see. Calculate delta S for the following reaction. And they give you the reaction, they give you the delta S values for each substance. So notice, I do want to point out one thing here. Oxygen is an element in its standard state. Right? Enthalpy of formation for oxygen in its standard state would be 0, or any element in its standard state would be 0. But that's not true for entropy. Entropy, you're going to have a value for that. So just kind of a reminder there. So we need to do products minus reactants. So let's add up, and you do need to take the coefficients into account. So we will do 4 times the value for NO2, which is 240.1, plus 6 times the value for water. And so those are our products, and then you will subtract the reactants. We have 4 times the value for NH3, plus 7 times the value for oxygen. So products minus reactants, and when you perform that operation, you get negative 114.4 joules per mole Kelvin. And so it's a negative value for our change in entropy. So that means it's getting less disordered or more ordered, which makes sense because you're going from 11 particles of a gas to 10 particles of a gas. So you're getting less disorganized there. Just one more example. This is a fake reaction with fake products and reactants, but calculate the delta S for the following. Again, you're going to do products minus reactants. We have 1C2, which is 191.6, plus 4 times the A2B, which is 188.1. So there are products minus the reactants, 2 times the value for A2B2, plus the value of just one C2A4, which is 121.1. And when you perform that calculation, you get that delta S is 603.7, and it's, of course, joules per mole Kelvin. And if we look at that, that's a positive value for delta S. So it's getting more disordered. And if we look at that, we're going from 3 particles of reactants to 5 particles of products. So that's making sense that it has more disorder. You're also going from liquids to gases, so that will affect it as well.